Before you build something, there are two ways of doing it. One is that you start to learn all the basics, and the other is you do the vice versa. You see something, you get the motivation to actually use it, build it, and then try to reach that objective. So I thought that it's great to put some sort of a benchmark. So let's see it in action.
I'm Emily Chang. This is Bloomberg Technology from San Francisco. In a moment, we'll be talking to Techonomy CEO David Kirkpatrick about the social media phenomenon sweeping the vegan meat industry. But first, we have seafood founder and CEO Jin Yang. Sorry, Mr. Jin, Mr. Yang?
It's a Mr. Jin Yang.
Okay. Mr. Jin Yang, you just sold your company Seafood to Periscope, and we're hearing the deal closed at over $15 million. Can you confirm?
I am a very rich.
My sources at Periscope tell me the tech is quite impressive, and your app uses the same machine learning to recognize if a food is a hot dog?
And a not hot dog. It's very important. It's a hot dog, not hot dog. It's technology.
Excited to see it in the App Store. I'm told it's releasing today.
For free? Because I'm rich.
Speaking of...
So the aim we have is how to be like Jin Yang and what Jin Yang must need to know to get to that 15 million mark. I think that's what we want to end up our presentation with. So, hi, I'm Anirudh Koul. I'm still learning how to use PowerPoint, but that's great. So hi, I'm Anirudh Koul. I'll be guiding you towards how to practically bring deep learning on mobile, squeeze it down so it runs efficiently, and get your production apps out there fast. I'm the head of artificial intelligence and research at IRA, where we try to use deep learning to help people with visual impairments. So imagine if you have a camera which is connected to an agent behind the scenes who can describe things to you. But if you try to use this human behavior to label data and do some things that could enable a blind person to live a more independent life. So that's what we do at IRA. Previously, I was at Microsoft, and I was the founder of Seeing AI, which is an AI app often considered the de facto app used by most blind users around the world. So during this journey at Microsoft, a common need was how to run things often on device, from the HoloLens to, if you're building an autonomous robot, how to run it on something which doesn't have a big memory footprint. So some of the learnings from that is coming out soon in a book called Practical Deep Learning for Cloud and Mobile, with my co-authors Siddha Benju and Meher Kasam. Siddha is an autonomous vehicle architect at NVIDIA, and Meher Kasam is an award-winning app developer who's currently at Square. And so we thought that all the things that we have learned in the last 5 years, how about we bring it down and distill it down into one book? So you can go from early stages where you can make things without coding, all the way to getting your PhD in compressing deep neural networks. So first of all, why run deep neural networks on mobile when you have cloud? Well, the first thing is that reduce latency, reduce time to not send the data through the network, and make a more interactive application. And secondly is privacy. You have GDPR coming up. It's already gone. So you have to always think about how to make less use of the user's data. And if you can do it on the device itself, users would be happy, law would be happy, government would be happy. And this brings to an important point about latency. There's a law of powers of 10, which shows, this was used also in the search engine land, which is when you get something slow, when does the user start to feel it's something real time? And when does it feel so laggy that they lose interest in your application? 10 seconds is what keeps a user's attention. 1 second is what keeps the user's flow of thought if you're using something. And 0.1 is considered to be reacting instantly. So 0.1 is what? 10 frames per second. So our job today is to be 10 frames or more on the device. Well, so for any deep learning recipe, you need two things. One is an inference engine, and the second is a pre-trained model to run to make your deep learning app. So we'll go over them and see how Jin Yang might have also done it and save some time. And a good way of structuring this presentation is maybe through platforms, maybe through architectures, or maybe through how long it would take to build you something. Because you want instant gratification, so how to get something done quickly. So building a deep learning app in X time let's say 1 hour. You had 1 hour. You had to impress your boss. What would you do? Well, you'll use a cloud application, right? There are a bunch of these from Microsoft, Clarifia, Google Cloud Vision, IBM, Amazon, and more. So the question that comes to mind is, there are all these great big giant players. Who do you select? That's a question, and for that you need a benchmark. Now in research you have ImageNet, Coco, and all others, but you haven't seen benchmarks of cloud services done with that. So we said, how about we make a benchmark and open source it, in some time as the book comes out, where you can try it out on your application and see what kind of metrics you get. So we said, let's try text reading, OCR, and image tagging. But text reading, taking scanned pieces of paper is going to give you the same results no matter what you use, plus minus 1 or 2% here. Let's go a little bit harder. So we selected Coco text. This is text in complete wild. Imagine somebody shirt writing a message on it, right? Can the system detect text on it? I think that's the kind of question we are trying to do. So in this example, you see text on billboards, on protesters, signatures. So let's try it on that. So first of all, if you had to build a system which takes 1 query per second, right, and you run it for a month, how much cost do you have to pay? Now 1 query per second is considered a decent big amount for most companies. But you can see that at the starting, you just have to spend $2,000. That's kind of like going to an O'Reilly conference every month. Save money there, spend it here, right? So you can see the distribution of some services are more expensive, that's fine. But the real question is, do you get quality? So we tested that. So using this benchmark of text, we ran it through Amazon, Google, and Microsoft, and found, considering this is a hard data set, who does better. And we found that you can see from 33 for Google to 45% for Amazon to 55% for cognitive services. So the key thing here is that as most of these systems are going from basic classical vision-based OCRs to deep learning-based, their reliability is actually getting better and better. This gives a good benchmark behind the scenes that you can replicate on your own. So the second question is image tagging. How good does people do in image tagging? We tried that. And Google and Microsoft were in the 49 to 50%, and Amazon was giving 65%. And seeing somebody so high up, it always becomes suspicious. Maybe we have done something wrong in the benchmark. So we looked around, and we found that the average number of tags that Amazon gives is way higher. So if you, as a matter of recall, if you give more things, chances that you would actually match with the tag that you have in your ground truth might match. So we didn't use exact word matches here. We actually used similarity match. It was interesting that Google actually goes down pretty deep. So instead of saying person, it would say military officer. So to find it for this benchmark, we had to make the concept similar using ConceptNet. And the benchmark is a little bit flawed there, primarily because we took Coco, which has 80 tags, and then compared it with other services which can give up to thousands of tags, which might or might not always match. But this is a good starting point that you can replicate on your data set, and that's the key point. So that's great. There's a cloud service. You can get your app done with a simple API in under an hour. Great. Well, hold on. If you're using cloud, there are some optimizations that you can use. For example, if you're using OCR, don't resize it down. Resizing is bad for it because OCR always requires a minimum length in height of the text. So instead, just reduce down, compress your document by 90%, and you would still not see much issues, much reduction in your accuracy. Now try doing that with image recognition. There's a different world out there. For image recognition, object tagging, you can actually reduce it down to something like 224 into 224. And you can compress it to something around 50% because neural networks are, robust to noise. That's what they introduced during training, and that is something that's helpful. Important thing to notice is also the interpolation you use. So base interpolation, the linear interpolation might not give you the best results, so try something like bilinear. It's always a good idea to resize it down and see for your application. If you're trying to recognize barcodes, going linearly down is a bad idea because The DNN won't be able to see straight lines of the barcode as an example. So some things to keep in mind. And keep your camera ready because some cool stuff will keep coming up. So the second question is you now have a day. Your boss is impressed. He says, or she says, go ahead and actually build it running on the device. Well, the first thing you need, well, obviously, training on the device is not going to happen. It's going to take logs and logs of firepower. But the energy it would take to run is very low on a device. So the first thing you start with is a pre-trained network. You have a bunch of these available. We'll go down into which is better as time comes over. And then you need an inference engine. Many players have been introducing it. So over the last 3 years, I have given this presentation in a different way every year. And most of the names that used to be on these slides have actually just washed away. They don't exist because they were GitHub projects which the community support well kind of dwindled, right? But now you have something that we can actually give serious recommendations on using your production apps. So let's get into the Apple's ecosystem. Well, things don't happen overnight. So Apple has, over years tried to give you services. For example, on the phone, on iOS 8, you had Metal. So most people who make video games try to use Metal to make their games faster. But you could use the same operators within it to, train your neural networks. Well, in 2014, nobody was doing it, but few people were. For example, Jetpack. In 2016, Apple introduced basic neural network subroutine and Metal performance shaders. So now what happens is they are giving you, this is a convolution operation. This is a node in your neural network, and you can join them together and build things. That was the idea. Very helpful, very fast. Only issue is that you had to hard code your network in your code. Imagine I give you a new updated architecture. Would you actually go back to your code and actually reprogram the whole thing in code? Well, things evolve. So in 2017 came CoreML. Now things became drag and drop. So you simply take a model, let's say you have in Caffe or you have in Keras, write 3 lines of code to convert it into CoreML, and just drag that CoreML model into your app. Makes life easy. Underneath the hood, it's taking care of all the understanding of whether to run something on a GPU, whether to run it on the CPU, and make things fast for you. And this was like the beginning of many awesome apps that have come out in the market. And in 2018 came CoreML 2. So the question was, can you make it more improved? And things like quantization for models, how to process multiple images or multiple steps together in batch, and also support for more frameworks, for example, Onyx protocol, so that you could use PyTorch or Caffe or Chainer and work on Apple's ecosystem by bringing your models in. One interesting thing that happened is that they also introduced Theory Create. I forget the name, what it's currently called. But you could transfer learn a model, but you don't have to put the whole model in. So iOS 12 comes with models till the featureizer level, and all you need to do is just put the fully connected layer at the end. So you just need to train this part and ship it with your app. So instead of having to send a 100 MB model, you are now sending a 75 KB model. How cool is that? Your app size is going small. And that's the kind of things that you want to use for making your stuff. All right. The other cool thing that happened is players in the industry started working together. For example, Google and Apple collaborated to release TF Core ML. So your TensorFlow models can now directly be converted into Apple's ecosystem with one line. Happiness around. Well, so my friends went ahead and benchmarked it on different phones. Well, when you ship to your users, you don't have a person twiddling their thumbs on an iPhone 10. They are waiting on probably a 3-year-old phone, a 4-year phone. So if you're sending a model to your people in, let's say, in a third world country, you want to be able to support as older a user. So if you use this benchmark, you can see that maybe if you want higher accuracy, you can ship a better quality model like, let's say, ResNet 50 or Inception v3 on, let's say, an iPhone 10 and still get 78 milliseconds. But if you're sending it on, like, let's say, a 4-year-old phone, you probably want to stick with SqueezeNet, obviously at a lower accuracy. Another interesting thing to note is in 2015, something happened. look at the numbers going from 2014 to 2015. More GPU technology came into the chips. So things started to actually parallelize inside and run faster, and that's a boon for making any of these applications. So you can use this benchmark table when you're building your own apps, all right? Pushing out more frames than an art gallery. Now, what's happening on the Google landscape? So 2015 November, TensorFlow comes out. Well, it's the full deal. So you could go around, tinker around. Maybe you get successful after 100 Stack Overflow threads. And when you run it down, it's a big, bulky model. But congrats, you're successful. So in 2016, Pete Warden and his team go and release TensorFlow Mobile, along with a book that came last year called Building Mobile Applications with TensorFlow. This is more optimized. It's taking care of many of the steps to be able to run more efficiently on a phone. But at the end of the day, it's actually still the real TensorFlow. So when TensorFlow was originally built, it's an afterthought to come and run it on TensorFlow on the mobile. So the question came, what can be done to run it faster and more specifically developed for the mobile? And so in 2018, TensorFlow Lite came around and actually matured. Smaller, faster. It has minimal dependencies, so you can package things easier and deploy. And also, you can write your own custom runtimes. If you tried something like TensorFlow Lite earlier this year, many of the very basic operators were missing. But now people have contributed and have been able to run things. And if you use, let's say, Keras, it takes one line to convert your Keras model into TensorFlow Lite. That's good. So I said it's smaller. What does it mean by smaller? The core interpreter is 75 KB in size. So imagine shipping this core interpreter into your app. It's not bulking up the size. If you add all the other necessary operations, it goes over to 400 KB. That's a boon. It's also fast. So if you are on a new Android, it has Android. It takes care of abstractions for running things with hardware acceleration. If you have a Snapdragon phone, there's a partnership where Snapdragon has its own DSPs and hardware acceleration. And this stack will take care of all that. You as a developer don't need to know much about it. Secondly, it's using flat buffers. So the key idea being how to serialize a file and deserialize it. It takes a lot of time. So this specific format, which is primarily built for games, is now being used on the mobile to reduce CPU cycles in serialization, deserialization, startup time, as well as reduce the memory usage when things get loaded up. Finally, imagine in your CNN you have batch normalization. You don't need to compute a convolution and a batch normalization layer one step after a time. How about you fuse it together? That's done here. And finally, instead of having dynamic memory graphs, it's now static. So it's already decided what you need to run at the end. And it's all taken care of automatically. As a developer, it takes you a few lines of code to get it running. This is basically an architecture of getting to the hardware level. You are at the very top of the stack. And whether you are running it on Android or you are running it on iOS, well, both run. We are currently benchmarking what happens if you run the same model on CoreML versus running it using TensorFlow Lite. So the benchmarks should be out soon. But the question comes again is, you want benchmarks. You have a model. Which phone do you want to work on? There are hundreds of models. So you can go to numerical.com, and they have a benchmark where several phones have been run through. And you can see, if you, let's say, pick a Pixel 2, and you have a MobileNet based app, it's going to run at 8+ frames per second. So that's good news. This way, you can go and plan out in which countries you are rolling, which are the main phones in there, and decide which models to roll out. There's another app called AI Benchmark. This was started out as a crowdsourcing benchmarking thing like Geekbench, but for AI. In this specific case, it's not one test of recognition, but about 9 tests, all the way from segmentation, super resolution, face recognition. So depending on your needs, you might want to consult this chart. Finally, there's Cafe 2 from Facebook, and it does some pretty neat stuff. It was also built with the main aim of being able to run the main Facebook app. So as you see, all the Snapchat filters or all the object recognition so that you can put AR filters on top of it, it's been built with Caffe too. And underneath the hood, they have, again, partnership with Snapdragon to make things run fast. On iOS, they use Metal performance shaders. And on ARM CPUs, they use Neon kernels to run things fast. Alrighty. Now, what's the recommendation if you're starting today? Train your thing in Keras. Easy. It takes one line to convert using CoreML tools to CoreML and make your app. It takes one line to run it and convert it and run it on TensorFlow Lite. How easy could it be? So now here comes the common question. First question, my app has become too big. Users cannot download it because on App Store you have a 150 MB limit to download on cell phones, so you have to go to a Wi-Fi connection to download it. One of the ways is that you don't package your model inside the app. Instead, you keep it on a server as a resource, let the user decide when they have to download it, and then compile it on the device. So there's 0 MB change at the starting, but you're reaping the benefits eventually. So that's one way to reduce friction. Second question is, you are a data scientist. You have an app today with a model. You update the model to be better. But in the app landscape, you actually have to package it back and then ship it. And shipping is like a hard thing. There's a lot of overhead. It has to go through approvals from Apple, which is minimum 2 days, and it used to be like 7+ days. You don't want to do that. So one of the ways is, again, you keep your model on the server as a resource, and let the phone actually check if the model has been changed, or maybe make a push notification, and again, download and compile on device. Now, this is a problem. Do you actually want to go and code this? Maybe no. So there are startups and companies which have made model managers. Google has MLKit. Fritz is another one, fritz.ai, and numerical.ai. And you can try them because they give you analytics of how users are using it, and you just have to press one button to say release this, and it gets deployed to all your thousands to millions of users with one click. So that's neat. Last question, and this will happen. You will make an app, and then it turns out that the bottom part of your screen is not recognizing. It's not recognizing the object that you intended it to be. Similarly at the top. And the common reason is that when the phone is by default cropping the middle square and missing out the top and the bottom. So you might have to squeeze, and depending on TensorFlow or CoreML, it's like a one-line change to make that happen. So warning, now you know. All right, so you're good at actually taking a pre-trained network, getting it running. You have got that art. You probably now want to train your own models. And that's kind of the whole area of transfer learning. If you know how to play an accordion, if you don't know how to play an accordion, it will probably take you 3 months to learn it from scratch. But if you know how to play a piano, you just fine-tune the skills and get it done in 1 week. And that's the whole area of transfer learning, which I assume many of you already know. So I will go quickly over it, but the whole idea is that take a pre-trained network for most things you want to do. Don't start from scratch. Don't be a hero, as Andre Karpathy says. But here's another important reason. If you train from scratch, you will not probably get the kind of accuracy that you can get from a pre-trained model. A pre-trained model might have seen a lot more. So the chances of overtraining on your data set actually get lower if you fine-tune it on a given, on your particular data set. So where do you get your pre-trained models? There's a search for modelzoo.co, which has 300+ models, all the way from reinforcement learning to pose to more. So have a look at it. Now I'm going to quickly skip over this because how you fine-tune depends on how much data do you have, and I think this table says it, but I'm assuming many of you know it. If you don't, I can explain it later on. But the key reason why I was actually showing this was people using Keras will use, transfer learning is one of the first tutorials that you see if you use Keras or pretty much any package, right? And it's going to take time. But there are services out where you don't even have to code, and you can get that final mobile model without writing a single line of code, even a few minutes. So Microsoft has custom vision.ai, where you just drag and drop 30 photographs, and it will train a model for you in under a minute, and then give you a CoreML or a TensorFlow Lite file that you can stick it into your app. Google has AutoML. The good thing with this is that it has full fine-tuning of your app. So if you have noticed that if you train using AutoML, the more you train, the more number of hours you keep it running, the better it will keep going. So it depends on you how good you want to have, and maybe it can help you know that whether you have enough data or not. IBM Watson has visual recognition, so it also gives you mobile models. And Baidu just recently launched EasyDL, which has something interesting, which is custom sound recognition, which others don't. So give them a try. One thing is if you want to actually get a bunch of photographs quickly, I recommend this extension called FatCun. It comes in Chrome, and I think in Firefox also. You go to your favorite search engine, open Creative Commons photographs, press a button, and it'll actually download those Creative Commons photographs onto your hard disk. So in a minute, you have 100 photos right there. Makes life easy. And you then stick that model inside your app, and it should hopefully start to recognize things. Alrighty. So I wanted to mention a quick story of, we are trying to train data, but sometimes you have to collect things. So quick story was, we are building for the Seeing AI app for blind users, we are building a barcode recognizer. And the idea was, the idea was that blind users don't know where the barcode is, so how will they even scan it? It's a very common need. So we put some audible barcodes, which means that if a barcode is visible, it starts to make a beeping sound. Let's skip it.
$5 US, $10 US.
Right, so it's running at, this one is currency recognition, 40 frames per second. Important note, you cannot be 99% accurate for currency recognition for a blind person. You have to go higher. So one of the challenges was, how do you get all this data in all shapes and forms? You want data. So we asked a bunch of volunteers back when I was at Microsoft to give this data. And we made an app called Edify. The whole idea was to teach with bad data. And we asked people to take a currency note and move it in as many ways, but give us dirty data. So you select something, and people would basically crowdsource and start collecting it. But notice it's not the kind of data you see on the internet. It's bad. It's crumpled, right? Alrighty. So we asked people to do that, but people still gave us very clean, simple front currency notes. They didn't understand what we meant by bad. So what we did is we took the worst photographs people sent to us, manually going through it, and we sent it out in a newsletter saying, can you do worse than this? And then people start to get competing in who can do a worse photograph than yesterday. So people start to take photographs like this, right? And photographs like this. And when we started to visualize our neural network, it started to pick patterns that I, as a sighted person, have never seen. For example, in that $20 note, there is actually this mini 2020, 2020, 2020 written for counterfeit currency detection, which I never knew, but my neural network started to pick up. And so our neural network started to get more supernatural. So think of an innovative way of collecting photos, and it works out. Now, alrighty, you know how to run the platform. You know how to train models. Life is good. But you want to ship something in production, which means you need to go fast. So let's get at how to make things faster. Well, life is like we have all this painful experience in real life. What you really want is not what you can afford. You have budgets. Similarly, neural networks, your phone might not be able to afford that budget. So as researchers started to go deep, deep, and deeper, and even deeper, ultra deep, this is kind of like the big data of deep neural networks. So researchers are working hard on increasing the accuracy. That's great. Everybody should. It gets you the best research papers at one point. But now in 2018, it's about production. even if you don't run it on a smartphone, you still would want your production code on a server to be as fast as possible, right? So what we as practitioners want not to be on the sides that I'm just marking out, which is 0.5 gigabyte big models, but somewhere in that green line where you have high accuracy, but also having less floating point operations, right? So phones are getting better and better. Your recent iPhone 10 is actually more powerful than MacBook Pro from 2017. Hooyah. Right? So what are the strategies that you can actually use to, in the budget of your user's phone, get things to run? So obviously you want to pick an efficient architecture, or you want, before training, design your own architecture. But after training, you can do pruning, quantization, and network binarization, which I'll quickly go into. So remember this chart? The reason why I bring this chart back is so that you can see the floating points, the million multiple adds. So VGG back was at 15,000 million multiplications and additions, whereas something like MobileNet is going closer to 500. That's great. And that's what will sell your app to win faster. So the MobileNet family that came out in 2017 has probably been the favorite one so far. It introduced something called as, it introduced depth-wise convolution and point-wise convolutions so that you can so you can decompose bigger matrices, the multiplication it takes, into smaller ones, which is more efficient. So instead of having two giant matrices being multiplied, you can instead take this matrix and make it into a single dimension vector into a single dimension vector, which is much cheaper to multiply. And you can play around with, depending on your application, the depth multiplier and resolution multiplier to go to the particular accuracy or go to the speed that you want. But then MobileNet V2 came out this year, which is about 20 to 30% faster with the same levels of accuracy. So let's get into the fact that depending on your application, if you're running efficient classification, you should pick MobileNet V2 these days. It's there in Keras, so again, you can convert it in one line. For detection, MobileNet again becomes like a good standard featureizer to build your detection application on top. So this is the chart with many architectures and with SSD and faster RCNN to see the level of mean average precision you want versus the speed it takes. Obviously, if you want to be too good, you'll be slow, right? But this year with MobileNet V2, and also on SSD with some optimizations done, and it's available in TensorFlow Lite, you can actually run things much faster and with a decent mean average precision. So you can go and check TensorFlow Object Detection API, and you'll find the SSD Lite, which is the special name given, with all the optimizations already built in, which I would recommend for using. If you're using segmentation, well, there's a bit of difference. So if you see a Snapchat filter or a Facebook filter, trying to take your face and segment it out, you can use cascading networks to basically pick and choose in a more efficient way and get real-time speeds. Now, one thing to remember is that when you do segmentation, you don't, and especially if you're doing it for faces, you don't need all the pixels. You can actually sample some of the pixels. And we'll soon see one of the things that can help you do that. And that thing is called dilated convolutions. So instead of basically reading like a 3 × 3 matrix, you can now read a 5 × 5 matrix, but skip each alternate row or alternate column in the middle. So now you have a much wider field of view to look at things. You can replace an n into n convolution with n into 1 and 1 into n, as I previously talked about. Depth-wise separable convolutions, which came from inspired by MobileNet. MobileNet 2 inspired inverted residual blocks. And finally, I'll get into another example. So if you have a large convolution, like 5 into 5 or 7 into 7, you can decompose it down into a series of matrices. So for example, instead of 1 7 into 7 convolution, you can have 3 into 3 convolutions. Now, neural networks are all dependent on non-linearity. So the more layers you have, the higher the accuracy. But if you can be faster and actually get better accuracy, great. And that's one of the ways you can do that: better, faster, stronger. Another thing is selective training. So this comes from what the app used to be, which is called Google Translate today. The idea was that if you're, let's say, taking a face app, right? Don't go and rotate the face while training at 180 degrees or 360 degrees. It's not going to help you. You probably want to rotate your photographs while training by like plus 45 to minus 45 and let the phone handle the orientation. So train for the case that you have at the end of the day, not for everything, which would just increase the size of your neural network. That's one trick you can use. Word length, that's the name. You'll often see the name pruning in literature, which is basically that if you have a node which is near 0 value, it probably adds no value. So why don't you just remove that node which has a value 0? Or nodes that are near 0 value, near 0, that's the keyword. If you remove them, you will be able to compress your network. That's the idea, right? Now, it doesn't work in practice. It's great in theory. It gets a great research paper out. But it makes your network sparse. And how are you going to run a sparse network? You need a new inference engine. So that's the no-no, I would say, where it makes great theory but not as great practice. But we'll get to a more practical solution soon. In lieu of time, I'll get to the other idea is also about weight sharing. So you know how in compression you have a pattern that's repeating. How about you form some sort of a code that's repeating often enough, and you are able to represent your network in a series of codes. That compresses also, but doesn't work on every phone because you don't have an inference engine that specifically makes it. So what works? It's filter pruning. So imagine you have a series of a convolutional filter with, let's say, 8 filters or let's say 16 filters. Not all the filters actually have the same weight. Some of them are literally worthless. So how about you remove those, and your network will just become thinner. So you can look at, does this layer actually have any effect on my final prediction? If not, while training, throw this away, and things just magically become thinner. So check out ThinNet. Quantization means going from 32 bits to 16 bits to 8 bits. In CoreML, it's 2 lines of code to get to 16 bits and barely touches any accuracy. But this year, they actually introduced to go to 8 bits, 2 bits, 1 bit. Now, your accuracy will have a dramatic loss, but you have the power. And that takes to the complete extreme side, which is how about you get to 1 bit? You see, if you use normal math of convolutions, you have plus, minus, multiplication. That's one way of doing things. The other way is that you binarize your network, not just the weights, but also the operations in there, and you're able to get much higher savings. So if you have a 32-bit thing, if you reduce it to 1 bit, that's like 32x savings right there. But interestingly, using something called ZORNets, you can get to about 60x speedups. In fact, that's a whole company out there. Remember we started with saying that we want something that gets us good venture money? This is Zornet, which are basically introducing a way to download models that run efficiently and fast. Now, one quick thing I will mention, which goes from research to production, is in research, you are working on a data set. It looks magical. You get the numbers. But if you actually just take ImageNet and try to just move your phone by 2 degrees here and 2 pixels here, you might actually have a dramatically different value in the values you see for prediction. For example, in this chair, you actually start to predict it's a motorcycle, and that's a problem. So what you want to do is do something where you average it out, your predictions. And there's a paper called CortexNet from Princeton, which actually does that and get better values. So again, not theory, but go to production. All right, as I'm about to end, we all wanted to raise some money at the end, saving, making some money out things, right? Well, XNOR did exactly that, so good luck to them. But here are a couple of things that you can get some inspiration. There are competitions like Low Power Image Recognition Challenge, CVPR, and others like EDLDC and System Design Contest. at DAC, which you should follow to get some inspiration. And this is the most exciting thing that I'll talk today, which is how about you let AI make your AI architecture, right? So check out MNASNet, Mobile Network Architecture Search Network. Now, there is a lot of papers. If you go on GitHub and search for AutoKeras, it's basically given your data, it automatically makes your network for you. It's exciting, right? But now, if you actually, in your objective function, actually introduce the latency of the model of how slow things runs by actually putting a real phone. So if you want to run on iPhone, put an iPhone. If you want to run it on Pixel, do that. And by adding that as one of the things in your objective function, the system would automatically make a network which is efficient for the mobile phone. And that's great to have. It runs on your particular architecture. So that system is actually beating the state-of-art networks so far, amazingly. And it's running 1.5 faster than MobileNet v2. So it runs in production. That's what you want to know. Well, robots are taking over the world. Get used to it. So I think everybody has one last question. I saw many of you taking photographs. You wanted this information. How can you get? Here's the short answer. How to access slides in 1 second. Go to @Anirudh Koul. You'll see the slides already out there. And just press the retweet button. And if you liked it, please let me know. So eventually, you will have all the things, but much better distilled out in this book, Practical Deep Learning for Cloud and Mobile. I'm Anirudh Koul, along with Meher Kasam and Siddha Ganchu, and thank you. And I should add one thing. Well, the reason I was talking about all this is because we are trying to run things efficiently on mobile, all the way from visual question answering to human pose detection. And we want to run it on mobile to help blind users. So if somebody is looking for opportunities at IRA, we are here. Thank you.